Thank you for watching, and welcome to LAQV Webinars, a webinar series on topics of green chemistry. For more information, visit our website and follow us on social media.
My name is Liliana Gomes, and today I will talk to you about naphthalimide-based chemosensors that are able to chelate and detect cadmium at physiological pH. The focus of my thesis is to synthesize and to characterize molecules that are able to detect metals. So as you know, cadmium is a heavy metal, and the problem is when this metal contaminate water or food, and people like us and other living beings consume this food or water, and cadmium becomes bioaccumulated in our bodies. This could lead to severe diseases. An example of this and how this happens is present here, because after many years using fertilizers, cadmium that normally is in residual amounts becomes accumulated in the soil. And with agriculture, the plants are growing, and in this case, rice can be enriched with cadmium. This is a problem because once we eat this type of rice, some diseases, and in this case, hepatitis disease, can manifest in cell. Of course, this disease, we don't hear it much here in Europe, but it's a problem in some countries of Asia because it is not really for its concentration in some foods. So the conventional method to detect this type of metals, it's mass spectroscopy, but is expensive and also time consuming. And we are hoping to have a new technique to avoid this type of problems. And I present to you the fluorescent chemosensors. And in this case, fluorescence allow us to have high sensitivity and easy detection, and also it's non-destructive and non-invasive. But what is a fluorescent chemosensor? In this case, it's a molecule that, when it's in the presence of an analyte, in this case a metal, it produces a different signal from the original one. Of course, in this case, I'm talking about fluorescence. This type of molecules, normally they present two different moieties in its structure, and we have the fluorophore moiety here. In this case, it's the naphthalimide, and this moiety is the one that is responsible by the rising, for instance, of the fluorescence. And then we have also other moiety that is the receptor. In this case, a nasochrome, and this is the part of the molecule that is able to interact with the metal. But why naphthalamides? We choose this compound, this fluorophore, because it allows us to have high quantum yields. This is important because we want to have a signal, a noticeable signal, to quantify and also to detect our metals in this case. And we are also using this fluorophore because it presents excellent photostability, so it's stable in the presence of light, and it allows us to have tunability in the system. It means that when we are extending our pi system, we can change the wavelength of emission and absorption, of course. Also, when we functionalize our molecule with a receptor, for instance, a receptor that we know that have a specific type of metal, we can also conduct our molecule to detect a metal that we have in our minds. And this is the part that we are doing here in this work. So now I present to you the naphthalimide fluorophore family that I will talk to you in this work. And as you can see here, I present you three different molecules, and the difference between them, they are azecron moiety. So you have the difference on the size from this here that you are seeing here in the left part of to the middle part. And also we have an extra difference in the azecron, that is the screen presents the system with less of a preliminary test that we conduct, that is our molecule in the presence of several metals. And in the left part of the screen, you are able to see that our molecule is almost non-fluorescent in the presence of several metals, but we have a slight increase of the fluorescence in the presence of cadmium. This is good because we have a molecule that is selective, but also it's not really good in a way because it presents a low intensity of fluorescence, and it makes